Hello students, today we will discuss and experiment on the some of the facts of simple pendulum. So first I will highlight the facts, then I will come to the theory part, and then finally I will demonstrate the experiment. And if you are okay with the theory, then you can directly go to the experiment, because it is important to visualize the theoretical concepts from experiment. Then I bet you will never forget these concepts. So let's do it. So basically a simple pendulum is basically a mass, let's say with a mass m, hanged from a fixed location position with a nearly massless string with, let's say, with length L, and it will execute a simple harmonic motion as shown in this video. Alright, now the fact on this simple pendulum is the time period of the simple pendulum. The time period of simple pendulum can be written as T equal to twice pi root over of L by G, where L is the length of the string and G is the acceleration due to gravity. So this is the time period of oscillation for a simple pendulum. Now the two important facts on this simple pendulum time period is T is independent of mass. No matter how much you change the mass, in principle, if it doesn't lead to the break up or damage of the string, then basically the time period will not change. You increase the mass 2 times, 3 times, 4 times compared to the original mass, still the time period will not change. And second important thing is that fact is that this T is proportional to square root of L. That means T depends on L. So basically larger is the L, larger will be the time period, or smaller is the length of the string, smaller will be the time period. So these are the two facts about the time period of oscillation of a simple pendulum, and these are very interesting facts. Now it's good to know such facts from the experiment, so that we will never forget these concepts. And before going to the experiment, we will first discuss about the theory. Basically we will derive the time period, expression of this time period from a mathematical calculation, and then we will come to the experiment. So let's do the mathematics first. So consider the mass has gone to a angular displacement theta, which is small enough, around 15 degree, and which has certain importance, and it is easy to understand. I will not highlight much here. And under this condition, you see the only force will be acting on the object is mg, which can be split into two mutually perpendicular components, namely mg cos theta and mg sin theta. Now this mg cos theta will be acting opposite to the tension of the string T, and basically eventually at the equilibrium this will cancel each other. So the only driving force to execute the further simple harmonic oscillation is basically mg sin theta. This is the driving force to continue the simple harmonic oscillation. Now from the definition of a simple pendulum or simple harmonic motion, this force must be negative, because by the convention this force is assumed to be in the opposite to the displacement of the pendulum. So from the equation of motion of a simple pendulum, f equal to minus kx, we put, instead of f we will put minus mg sin theta, and this equal to minus mg sin theta equal to minus kx. So under the small angle approximation, this x can be written as L into theta. So and the sin theta can be also written as theta. So we have the relationship minus mg theta equal to minus kl theta. From this we get the expression of k, and that is mg by L. Now the time period of a simple harmonic motion is defined as t equal to twice pi by omega, where omega is the angular frequency and omega can be written as root over of k by m. So putting this value of omega, and then we find expression, and putting a value of k, then we find finally we find the expression of the time period, which is 2 pi root over of L by G. So this is the formula which we needed to derive, and we have derived now. Now from this formula, those two important conclusions, like the facts, and those are that t is independent of mass and t depends on the length. So these are the these are the facts which are apparent. So in precisely t should be proportional to square root of L. Basically larger L corresponds to larger t. So larger is the length of the string you make, then the time period will increase. Or on the other hand, if you smaller if you make that length smaller, then time period will also decrease accordingly. So these are the two facts, and we need to understand these facts from experiment. Okay, so for the experiment, I have prepared one simple pendulum which consisting of a metallic mass which is hanged from a fixed position, namely from the middle of the horizontal rod by a nearly massless string, metallic string, which is flexible as well. So this is our simple pendulum. Now this simple pendulum will make oscillations. So for the first we will count the total time for the 5 successive oscillations. So 2, 3, 4, 5. Okay, so for the 5 oscillations we have the total time taken is 7 second, around 7 second, and if we average out, then the time period of the one oscillation will be about 1.4 second. So this is our original pendulum, and it has this original time period. Fine. Now to check the first conclusion, that check the mass independence of the time period, then we are going to add additional mass on this system, and I am going to increase the mass approximately 5 times the compared to the original mass. I am adding more of this metallic pieces on it and attach it carefully so that it doesn't fall during the oscillation. Now I am going to calculate again same 5 oscillations now, and then average out to find the time period of one oscillation. So let's count it. One, 2, 3, 4, 5. Again you see, now even though we increase the mass at least 5 times compared to the original mass, still the time period remains same, which is around 1.4 second like previous. So time period is certainly mass independent. So you can check by yourself for the some other mass and check out this mass independency of the time period of oscillation for the simple pendulum motion. Now we will come to the second conclusion, that T is proportional to length. Smaller is the length, and then smaller will be the time period. So to do that, we have shortened the length of the string. Nearly 1/3 of the length has reduced. Now under these circumstance, we check out the time period of oscillation. So again we will count the 5 oscillations subsequently, and then we will average out to find the average time period now. So let's do it. One, 2, 3, 4, 5. So you see, for the 5 oscillations it took 5 seconds. So the average time period or time period for a single oscillation is 1 second, around 1 second. So this clearly shows that the time period has a length dependency. So you can also check this experiment for some other length. Thank you.